Power density is megawatts per square kilometer. How much power can you get out of a given area of a geothermal field? So when you're looking at it in map view, people will draw what they think the boundary of the reservoir is, and you can calculate how many megawatts you can get from that number of square kilometers if you have an idea of what the power density ought to be. More temperature, you get more power density. But there was this one or two fields that were very hot that didn't have very high power density.
Welcome to Geothermal Unleashed, where we will explore the cutting edge of geothermal energy. I'm Elizabeth Cambre from the Valorec New Energies team. I'm here to help educate and document geothermal's rise in the global energy transition. Today, I'm delighted to welcome my guest, Maxwell Wilmarth, the president and CEO of Maxwell Geothermal. So welcome to the show. Why don't we start, Max, with you giving us a little background on your history. You can talk about your education and your career and how you came to be a part of the geothermal industry.
All right. Hey, Elizabeth, thank you for having me. I really appreciate the invitation, and thanks to my boss for letting me come on Maxwell Geothermal. So my career arc, I can give you a quick rundown on that. I'll try to do a quicker job than I gave Nick Sestari before. So I'm from Sonoma County, California, a little town, and the Geysers geothermal field is right here in my backyard. That didn't come into play until much later, but I went to UC Berkeley and studied geology, got a bachelor's degree and a master's degree. And then after graduation, I did a few years in the environmental industry and then found out about the geothermal industry, and that the geysers that I had known about sort of tangentially was this biggest geothermal field in the world. And at the time, there was a boom going on in geothermal worldwide and also especially in Nevada. And I was able to get a job with a company that doesn't exist anymore called Nevada Geothermal Power out in Winnemucca, Nevada. And we were developing Blue Mountain, which is almost 50 megawatt power plant that's still in operation now. And then from Nevada Geothermal Power, I went to another company called Global Energy. GGE was based right here in Sonoma County in Santa Rosa, and had money from Mighty River Power in New Zealand. And the idea was Mighty River Power was going to do geothermal in New Zealand, and GGE was going to do geothermal everywhere else in the world. And GGE was staffed with a bunch of Unocal and Chevron veterans. So geologists and geothermal professionals like David Sussman, Glenn Melosh, Jim Stimac, Phil Cumming was instrumental to that because he's here in Santa Rosa, and others. And so I was really lucky to be able to have those guys as mentors relatively early on in my career. And we did a bunch of stuff, drilled 4 deep wells on top of a mountain in the Andes in southern Chile, and blizzards way up at 5,000 meters in the Altiplano in Chile. We also had projects in Peru and Germany and in the US. And the big thing that company did was invest in the Hudson Ranch project in the Salton Sea, which is the newest power plant in the Salton Sea, 50 megawatts. Now, Mighty River Power decided that they wanted to take everything in-house after about 5 years. And so I went and worked for them directly in New Zealand for a couple of years. And there I got blown away by the world-class geothermal fields that they have. And a new plant was coming online called Ngā Tamariki, which I was the first project geologist of the operating field. And we quickly had to drill a new well, which I targeted, and ended up being like a 40 megawatt well. It was crazy, but there were 3 other 40 megawatt wells in that field. It just shows you how unbelievably productive they are in New Zealand. And then after a couple of years, was missing home, so found a job back in California in San Francisco with Geologica and Jill Hazlett. And Jill hired me to be her senior geologist and eventually vice president of science. And the team was quite small at that point. I helped hire some of the people that are there now and build it up. But I was there for a few years, and Jill sent me all around the world as a consultant. And I was in Samoa and Kenya and Djibouti and Turkey and Armenia and a bunch of other places, but eventually spent a month in Indonesia. And when I was in Indonesia, I realized that this was really the hot place for geothermal because there were so many big fields, there were so many new projects happening, there were so many service providers there and universities and just a whole infrastructure of geothermal that it was the place to be for new projects. And so I found a job with Jacobs Engineering and became their manager for geoscience in Jakarta. And I opened up that division, and I had about 10 geologists and geophysicists and drilling engineers and well testing. And we worked on a variety of different projects in Indonesia for operating companies and developers and for state agencies for about 5 years. That was all during the pandemic. And again, got homesick and wanted to come home to California. And so I was able to catch on with baseload power and did a couple years with them, moving projects forward in Nevada. And then I decided to go independent just earlier this year and started Maxwell Geothermal. And I provide private consulting for investment decisions, for exploration, for well targeting, for resource capacity estimation, the whole gamut.
So Max, it seems that you were my first guest that's come on the podcast to talk about hydrothermal geothermal. I didn't realize that I have only been interviewing folks involved in next generation geothermal. So this excites me. So thank you for pointing that out. And I think then it makes sense if you could talk about what conventional hydrothermal geothermal is. Maybe give us a little bit of a background on this part of the industry within the US over the past decades.
Sure, yeah. So I've been in geothermal for about 20 years now, and I only a few years ago realized that I was in the hydrothermal industry
Okay.
because so much of the new activity is happening in EGS and AGS. So I like to give people the sort of a short 101 when I'm talking about what I do and what geothermal is. And so what I usually say is, so you know from grade school that the center of the earth is very, very hot, right? And it is very hot. It's the core, the center of the earth is as hot as the surface of the sun, which is about, it's over 5,000 degrees Kelvin. And everywhere on the earth is very, very hot, pretty shallow, maybe 50 kilometers down. If you could drill anywhere on the earth, you would get very high temperatures that you could do geothermal with. We don't notice it at the surface because the earth is covered in water, and that water is circulating through fractures and sandstone and stuff on the surface and cooling it off. And so we only really see it at volcanoes, at hot springs, and a few other places where we notice that heat coming out. And so the goal for drilling down and tapping into that temperature is to do it economically. And technically, physically, we can drill maybe 12 kilometers deep. I think that's the deepest well that was ever drilled in Russia, and they did it for scientific reasons. Realistically, we can drill maybe like 5 kilometers deep, maybe a little bit deeper with new technology economically. And I'm sure that's going to get deeper over time. But in hydrothermal, we normally would put a limit at about 2 to 3 kilometers, maybe 5 kilometers in special situations. And so we need to find places where that heat has come up that shallow. And that's going to be around volcanoes usually, or places where there are deep faults that allow hot water to circulate from that depth. And then after you find the temperature, the trick is to find permeability, because we need very, very high flow rates to move that hot water to the surface. The energy source is really the hot rock. And so something like 98% of the energy is in the hot rock. And to move it to the surface, you need water and steam, and a lot of it. So the flow rates that we need are an order of magnitude 10 times or more what you see in oil and gas. So in oil and gas, maybe an oil well is profitable at 100 barrels a day, depending on the price. But in geothermal, we need tons per hour or hundreds of tons an hour of hot water coming to the surface. So these are big cracks. And they don't exist everywhere naturally. They exist in places that have a lot of tectonic activity or are fractured for other reasons. And so oftentimes we'll find a place that is hot at those kind of depths, but we don't have the natural permeability, or it's very, very difficult to find. And so you're drilling a bunch of expensive wells that are dry holes before you actually find it. And there's a lot of innovation that has happened. It can still happen around that to reduce the number of dry holes and find that permeability cheaper and more easily. Of course, EGS and AGS, they often will want to have zero permeability and just have the high temperature so they can make their own. So they've solved that problem a different way. And then the other part of it is not as much technical, but is economic, is what is the competing power prices and are you near the grid? And so oftentimes countries, if they're happy to burn coal, then you're just not going to be able to compete with that. But otherwise, geothermal can be very cost competitive and very reliable, 24/7, 365, domestic. You don't have to rely on imports. Very low greenhouse gas or zero greenhouse gas emissions. I don't usually say it's zero because there's a little bit of natural CO2 in any underground water source. And so a little bit of that will come out, but it's very, very low compared to what the equivalent amount of electricity you would get from another type. And being near the grid. So you can have the best geothermal source in the world, but if it's 500 miles from the nearest power line, you're probably not going to develop it. There are some really interesting business opportunities right now for doing data centers and other users of the electricity, like green hydrogen, that can be off the grid. And so those are now in development. So that's kind of my short pitch.
Yeah. Okay. I've got a lot of questions for you.
Okay.
First, I want to ask you, last week you gave a presentation at the MPGS dinner, and you presented on power density, and this is one of your areas of expertise. Can you tell us what power density is and what goes into calculating this of a given area?
Yeah, so I'll summarize my talk that I gave last week in Reno to the Nevada Petroleum and Geothermal Society. We had about 50 people there. Thanks for everyone that came out. You can find that presentation online on my LinkedIn page. So power density is megawatts per square kilometer. How much power can you get out of a given area of a geothermal field? So when you're looking at it in map view, people will draw what they think the boundary of the reservoir is, and you can calculate how many megawatts you can get from that number of square kilometers if you have an idea of what the power density ought to be. Now, the best way to project or to estimate the number of megawatts, the resource capacity of a reservoir, is to have a lot of subsurface data, a lot of wells, so you really know what's down there. You can do a conceptual model and then a detailed numerical model that is going to be both wellbore coupled to your discretized reservoir model, and then a bunch of production history to match with it. Now, you absolutely don't have that in the exploration or development stage. You can't do that. So we rely on volumetric methods instead. Volumetric means this big volume of rock. How fractured up is it? How much energy can we get out of it? And so those are called heat and place estimates usually. And they're very valuable. And if done correctly, they can give you some good results and reliable numbers. Problem is that these models are very, very complicated. They're overdetermined usually with lots of degrees of freedom. And so there's lots of little knobs that you can tweak to get the number that you want. And people can go down the wrong rode with these very, very often and get unrealistically high estimates, like 10 times too much. So oftentimes I'll see like 150 degree C field in Nevada and an estimate of over 100 megawatts for the reservoir as like the median value, the most likely value. Like, well, there are none that are that big, maybe McGinnis Hills, but that shouldn't be the middle of your distribution. And so we use power density is a simpler method. It actually is basically a volumetric method, but assuming a reservoir thickness of uniform thickness. And I didn't invent this. The first person I know that really treated it was Malcolm Grant in New Zealand, and he looked at like 10 or 15 fields, and he noticed that with increasing reservoir temperature, you get higher power density, maybe 10 to 40 megawatts per square kilometer. Not very surprising. That's the energy source. So more of it, you get more temperature, you get more power density. But there was this one or two fields that were very hot but didn't have very high power density. And then I took it along with Jim Stimac and others to the next step, which was doing a lot more fields. So we did dozens and dozens of them. And then we defined the area very carefully. So previously, the area was whatever some geologist or somebody wanted to draw on the map. We said, no, it's a 500-meter buffered radius around the production well tracks, just the production wells, not injection wells. And so this couples the power that you're getting from your production wells with the area of those wells and gives you much more realistic numbers. And we did this for a bunch of different fields, and we noticed, yes, you do get more power density with higher temperature, and maybe it's actually on an exponential curve. And also that there seems to be a tectonic setting association with the lower temperature fields tend to be fault-based systems like you usually get in Nevada or Turkey or Germany, where there may be a few or only one fault that all the geothermal circulation is happening on and tends to be lower temperature, less than 200 degrees C. And then there's these fields that are very hot and very high power density, and they tend to be magmatic and in rift-like settings like the Salton Sea or the Salton Trough and the TVZ in New Zealand. And then in the middle is mostly populated by volcanic hosted geothermal fields of various types, where there's a specific volcano or group of volcanic vents that you can identify. And they are in a variety of tectonic